Hi, everyone. I'd like to share with you Lesson 12, Writing About Statistics. This is paired with a Blackboard PDF that you can read through that has the same code, and you can run it yourself. This week, I'd like to share how do you write factually accurate statements about statistics in a way that's readable and engaging. We need to communicate things that we've learned from our analyses to ordinary readers. So it's really important that we don't get really stuck in some of the details, but instead are able to describe our results very flowingly. To do so, I'm going to draw from the New York City flights data set, and we're going to practice reporting results from it. First, we're going to load the Tidyverse package, the NYC Flights 13 package, Modern Dive package, and the car package. So once we've done that, we can then try and ask a question. In this example, I'm going to model why some American Airlines flights going out of New York City airports, why they got more delayed than others in 2013. There are several ways of stating this question generally. First, why do some flights' arrivals get delayed more than others? Second, what key factor explains the variation in flights' arrival delays? Third, what explains the variation in the minutes of arrival days for a flight? And fourth, I modeled variation in the dependent variable, minutes of arrival delays per flight. So, I don't know about you, but 4 is pretty bad, right? You would have to know the dataset really well to understand that. Instead, I like number 1. It gets across the main idea, uses colloquial language, and implies that there is variation in the outcome, that some arrivals are more delayed than others. And it's short. So now we stated the question. How do we then start reporting how we modeled the data? So let's say we ran a model, and we're just going to look at just flights run by American Airlines. And we're going to do something similar to your homework where we're going to test, did you get bigger arrival delays if you departed later, if you were traveling further, or if you were leaving from one of 3 different airports. I think JFK and LaGuardia, and there's one more. And that's the baseline. Here are 3 ways to report this. I like the first one the best, and they get kind of worse as you go on. Do flights see greater arrival delays when they are more delayed when departing, when they travel further distances, or when they leave from one particular airport instead of another? That's a really nice way to introduce your predictors. Alternatively, I controlled for minutes of departure delay, distance traveled, and the airport each flight left from. Finally, as explanatory variables, I use departure delays, distance, and airport. I don't like that last one, right? I think that the first one is really good. And it's good because it structures the sentence. It gives readers a structure. It helps them know that each variable is different from the other, that there are different explanations, that they might each independently affect the minutes of arrival delays, the outcome. And it really poses it in human language. You could analyze this without statistics. And people would probably phrase it the same way. So that's good. So then how do we report the fit of our model? Well, so we can run the analysis using the summary function to get our model fit table. And you see we've got our model fit statistics here, like R squared, and the F statistic. Ooh. Well, good news. Our F statistic is off a little bit, but This must be from a previous version that I ran. So that's why this says 3,102 instead of 2,483. But don't worry about it. Okay, we're just going to keep on going. So here are 3 ways we could describe this table. This model had an R squared of 0.79 and an F statistic of, let's do the fixed one, 3,102, with a p-value of 2 times 10 to the negative 16th power. Not very good. Alternatively, this model explained 79% of the variation in the dependent variable and explained more data than the intercept would, with a p-value below 0.001. I mean, it's better, but it's not great, right? Finally, let's try this one. This model explains 79% of the variation in flight arrival delays, and it had a statistically significant fit, where we can put in parentheses, F equaled 3,102, and the p-value is less than 0.001. That's nice. That's very nice right there. It gets right to the point. It uses the terms, the variable names themselves, instead of things like the outcome. And it says it's statistically significant. Now, most readers won't really know what that means, but they'll be like, oh, it's statistically significant. That sounds good. And it is. And we're not just going to say it's statistically significant and then leave it. We're going to put in parentheses where p is less than 0.001, so that readers who do know statistics are going to know, like, oh, it's statistically significant. How significant is it? How low is the p-value? So we can entertain both audiences with this kind of writing. Okay, so how about model assumption tests? That one's a little trickier, right? Because model assumptions are, well, a little more complicated. Here are a few ways that you might discuss multicollinearity. First, we could run the variance inflation factor test. And remember that we're squaring that so that this column becomes comparable. It becomes on the normal scale. And we're doing that because we've got both numeric variables in here and because we have categorical variables in here. So that's good. So here's the thing. We could describe it like this. The variance inflation factor for each variable was under 2.5. To compare variance inflation factor scores for numeric and categorical variables, I got the generalized variance inflation factor for this test, taken to the 1 divided by 2 times the degrees of freedom power, then squared again. That's terrible. Oh my God, I don't even want to write that down. I cringed when writing it. Here's another way we could say it. To make sure my model did not have a multicollinearity problem, I calculated the variance inflation factor for each predictor in my model. Each variable's score was under 2.5. You know, that's not bad. It does simplify some things, and that's good. It also glosses over the fact that we transformed the variable, that we transformed the VIF test. And you know, like, I think that transparency is a good thing. So let's try a third one that explains more what is multicollinearity. When two variables in a model are highly correlated, the model can estimate incorrect effects on the outcome in what is called a multicollinearity problem. However, I calculated the variance inflation factor adjusted to be comparable for numeric variables like distance and categorical variables like airports. Each variable's score was under 2.5, the gold standard, and nowhere near 10, a problematic value. I really like this one. This is how I write it in my papers, because I tell them that I adjusted the VIF test. I tell them what a good VIF score is, what a bad VIF score is, and where ours was. And I also defined multicollinearity in a way that's pretty straightforward. I like this a lot, and I think it's really transparent. How about for independence of observations? This one was kind of hard to teach, let alone to report in easily understandable words. So how do we do this? Well, first, we could visualize whether we've got constant variance or non-constant variance. And just to recap, what is that again? Well, you can use the get regression points function. This is a different way to do the same thing that we've done in the past. What's nice is that get regression points just gives you the predicted values and the residuals in the same data frame. Does that make sense? So it's going to give you the residuals, so we pop them in right here, and it's going to give you the predicted values, and they're called whatever your outcome was with hat on the end for predicted. So we can make a scatter plot that looks like this. We have to reload this. Technical difficulties. Pardon the delay. All right. Wow, it really is having a moment here. Great, there we go. All right, so as we can see from here, we've got a pretty big fan shape going on. That's generally an indication of heteroskedasticity. However, if you use heteroskedasticity in the sentence, most likely you'll misspell it, and second, your readers will not know what it is. So we have a duty to put that into more understandable language. So what can we do? Well, we can take a moment, because finally I've actually got this right spot. Just a sec. Great. We could look at it like this. We could say, this model suffers from some heteroskedasticity. Our data has interdependence of observations because our data includes flights that went out at the same day, time, or month. As can be seen above, the residuals vary extremely from one predicted value to another, forming a fan shape. Doesn't do much for me. Let's try something else that really gets at the heart of what's going on and explains this visual. Because some flights leave at the same times and on the same days of the week, our observations depend on one another. Our predictions tend to be spot on for very large values like this, right? The residuals are very, very small. But they tend to have larger residuals when the predicted value approaches 0. Sorry, that should say approaches 0 right there. Right? Large residuals. That's really useful. That kind of is transparent. It tells us, hey, our model's like pretty good most of the time, but sometimes it's pretty bad, right? It describes heteroskedasticity very accurately without ever having to use the word. So that's a good thing to keep in mind. Last but not least, we really want to report coefficient tables. This is the big skill, because this is very useful for us. So for example, we could use the get regression table function to get our coefficient table, where we've got alpha and we've got the beta coefficient for departure delays and distance and for each different airport. And we've got the p-value right here. So if we did this, what could we do with this? We could say first, the beta coefficient for departure delays was 1.015 with a statistically significant p-value below 0.001. Also, the alpha coefficient was negative 8.587 with a p-value below 0.001. I don't like that very much. Let's try something else. The model indicates that flight's departure delays have a positive statistically significant effect on flight's arrival delays. Independent of distance traveled or which airport the flight left from, flights whose departures are delayed by 1 minute tend to arrive 1.015 minutes later. And we're going to put the statistical significance in brackets. And flights that had no departure delays, did not even leave the airport, and were not from JFK or LaGuardia, tended to arrive 8.587 minutes early. And we're going to put the p-value in there again. This is a pretty good way to talk about the the beta coefficient and the intercept. I mean, it is kind of funny. Like, what is a flight? How can you talk about the arrival delays of a flight that didn't even leave the airport? But it's a pretty good way of describing it. Whereas the first sentence we discussed was virtually incomprehensible, right? Your reader doesn't know what a beta coefficient is, let alone an alpha. So in closing, let's piece these sentences together into a useful paragraph. I'm going to read them aloud and take a moment to think about them. Why do some flights' arrivals get delayed more than others? Do flights see greater arrival delays when they, A, are more delayed when departing, B, when they travel further distances, skip that C part, or D, when they leave from one particular airport instead of another? This model explains 79% of the variation in flight arrival delays and had a statistically significant fit. When two variables in a model are highly correlated, the model can estimate incorrect effects on the outcome in what is called a multicollinearity problem. However, I calculated the variance inflation factor, adjusted to be comparable for numeric variables like distance and categorical variables like airports. Each variable's score was under 2.5, the gold standard, and nowhere near 10, a problematic value. Because some flights leave at the same times and on the same days of the weeks, our observations may depend on one another. Our predictions tend to be spot on for large values, but tend to have larger residuals when the predicted value approaches 0. The model indicates that flights' departure delays have a positive, statistically significant effect on flights' arrival delays. Independent of distance traveled, or which airport the flight left from, flights whose departures are delayed by 1 minute tend to arrive 1.015 minutes later. And flights that had no departure delays, did not even leave the airport, and were not from JFK or LaGuardia, they tended to arrive 8.57 minutes early. Not bad, right? So I would check out whatever analysis you want and try and practice this. Try writing this kind of paragraph, model it after this paragraph. You can do it with your with your preliminary results from your final project. Feel free to share them with me. Feel free to email me if you have any questions. And we can talk through some good strategies for writing about statistics. So thanks for your time, and look forward to seeing you again.